In this lecture, we're going to look at invariant diagrams for solving problems that contain three segments. A typical problem description might be as follows. Using an invariant diagram, specify and hence derive an order n solution to the following. Given an array f0 to n containing only zeros, ones and twos, sort it so that all zeros precede all ones and all ones precede all twos. And of course, only swap operations are allowed on the array. So the first thing we need to do is we need to write down a specification based on the English description that we've just been given. So our specification is going to contain a number of parts. It's going to contain any information that we have about constants, like n for defining the size of the array, and any assertions that we've been given about n. Now in this case, we have been given an array that contains zeros, ones and twos, so it would make sense to assert that n is greater than 0 in this case. An empty array could not contain zeros, ones and twos, so we need to ensure that n is greater than 0. Next, we need to define the variables that we have in our program. So, as well as defining the constants, we now define variables. And of course, our array is going to be defined as a variable instead of a constant. And the reason is because we will be sorting the array. The items in the array will change. One of the other things we can do is we can write an assertion about the contents of the array. We're guaranteed that the array contains zeros, ones and twos, so we can assert that it contains zeros, ones and twos by saying for all j greater than or equal to 0, less than n, so where j has an index range for the entire array, all those f.j's are either equal to 0, 1, or 2. Not necessarily in the correct order, but the array contains a mixture of zeros, ones and twos. The next thing, of course, is a label, some label s that represents the program. And the most important piece of the program specification is the post condition. So if we have an array and we want to split the array into three segments, we're going to need two variables. So here we define k and t, and we give k and t a range. K is greater than or equal to 0, and t is greater than or equal to k. So t can't be less than k, t is greater than or equal to k, but t is less than or equal to n. So we're defining an order here of between 0 and n. We have two variables k. K is going to be a variable between 0 and t is going to be a variable between k and n. Now with that setup, what we can do now is we can define three different segments of the array, and we can specify what each of those segments contains. So the first segment is this. So for all j, where j is greater than or equal to 0 and less than k, so where j is between 0 and k, this segment is going to be f.j equal to 0. Where j is between k and t, this segment is going to be f.j equal to 1. And where j is between t and n, this segment will be f.j equal to 2. So the first step in using an invariant diagram is to draw a diagram that represents the post condition. So I've rewritten the post condition here from our specification. And remember, it contains three segments. So this is the first segment here. We can see the second segment there and the third segment. So we just literally draw a diagram that represents those three segments. So where j is between 0 and k, well, that's all the zeros. Where j is between k and t, well, that's all the ones. And where j is between t and n, that's all the twos. And that's the first step along the way in using an invariant diagram. Just literally draw a diagram that represents your post condition. The next step is to draw an invariant diagram. So the invariant diagram is where we actually introduce a segment into our diagram that represents the unprocessed part. And to do that, we need to introduce a new variable. So in this case, I've introduced a new variable q. It doesn't matter what we call it, just once it doesn't conflict with any of the other variables that we have. So this new segment, and I've actually written it out here as a new segment in mathematical form. So this new segment between q and t is going to contain our unprocessed part of the array. So in here will be either zeros or ones or twos. Now pay particular attention to where the new variable q was introduced. It was introduced after k and before t. It needs to be here to make life easy for swapping values around and so on. So it's introduced after k and before t. Now that we have this segment that represents a snapshot of the middle of processing, we can use this to kind of roll backwards to see where k and t were at the beginning of processing, roll forwards to see where they are at the end of processing, and we can look at the particular steps we need to take in the middle of processing in order to figure out what our program will look like. So the first thing we do with our invariant diagram is we imagine what things would look like at the start of processing. So when we look at the invariant diagram, we see that we've got this unprocessed segment now between q and t. So what would happen if we imagine what this segment would be like at the beginning of processing? Well, at the beginning of processing, nothing has been done. The array has not been processed in any shape or form. So this segment between q and t would really be the entire array because we haven't processed anything yet. So if this segment between q and t represents the entire array, well then the only way to expand this segment is for q to go that way. And if q goes that way, k needs to go that way. And for t to go this way. And if we do that and roll backwards, bring q and k to the left and t to the right, well, k will be 0, q will be 0, and t will equal n. So this is what we have as our initialization for k, q, and t. So k and q will be 0 at the beginning of processing, and t will be equal to n at the beginning of processing. And that means that from k or q to t represents the entire array. So this segment from q to t represents the entire array at the beginning of processing. At the end of processing, well, we play the same game really. We look at the unprocessed segment again between q and t, and we say to ourselves, right, well, as we're processing this, as we have this snapshot of the middle of processing, what will happen? Well, this segment needs to shrink. It needs to get smaller each time we process a particular element. So q will hopefully go in this direction, and t will hopefully go in that direction to shrink this unprocessed segment. And if we Roll that forward, well then Q and T will meet in the middle somewhere. So if we draw a little diagram that represents this, that segment, that unprocessed segment, will eventually be of size 0 and Q will equal T. So therefore, at the end of processing, the segment FQT will be empty. That is, Q will equal T, and therefore the guard on our loop will be Q less than T. So we'll continue to process as long as Q is less than T. As long as this Q is less than T, we will be able to continue to process. When Q equals T, there'll be nothing left to process and we'll be finished. The next step is to look at the middle of processing. Now, as this is a 3-segment problem, there are 3 cases, because what we're processing could be a 1, it could be a 0, or it could be a 2. So in the middle of processing, we imagine with that we have each case and we see what we need to do in each case. So for the first example here in the middle of processing, we're going to imagine that the value at f.q is a 1. Now it actually doesn't matter what order you take this in, but the reason why I'm imagining f.q is a 1 because this is the easiest case. If we have a look and we imagine that f.q is a 1, well, we don't need to move it because it's already adjacent to or next to the segment of 1s. So it doesn't need to be moved. All we need to do is just kind of include this 1 in the 1 segment. And to do that, it's very simple. We just increment k to include, or increment q to include this 1. So what we say is that if f.q is equal to 1, we simply increase q by 1. So we say q becomes equal to q plus 1. Q moves forward 1, and now the 1 that was there is included in the segment of 1s. The next case that we're going to have a look at is if q is equal to 2, or sorry, f.q is equal to 2. Now in this case, it's obviously not in the right place. It needs to be included over here in this segment of 2s. The only place we can put it really is here. So we need to do a swap. So in the diagram down here, I've shown you what's happening. We are going to do a swap. And the swap will take the value 2 from here. We know that f.q is the value 2. And we're going to put that over here where it should be. And we're going to take this unknown quantity, this unknown value from there, and we're going to swap it back into f.q. Once we do that, we now know that there's a 2 here. And what we need to do is decrement t. So the code to do that, we'll have a swap operation that will swap f.q with f.t minus 1. And then we'll decrement t. Finally, if f.q is a 0, well then, once again, it's not in the right place. So what we really need to do is we need to join this f.q value, which is 0, and we want to put it in beside all the other zeros here. So where can we put it? Well, in the diagram down here, we show what we need to do. So we know that we have a 0 here, and we need to add it on to the other end of the zeros over here. Now there's a 1 currently at f.k, so we can take the 0 and put the 0 where this f.k value is, which is a 1, and we can take the 1 from there and just append it to the end of the 1s. Now once we do that, there are two things that we need to do. We've just put a 0 in here, so the segment of zeros needs to grow by 1. K needs to go in this direction, so K needs to be incremented. Also, what we've done is we've taken the 1 from here and we have put it over here where there was a 0. So the segment of 1s needs to grow. The segment of 1s hasn't gotten any bigger, it's just kind of shifted rightwards in the array. So we need to increment Q in this direction as well. So we do the swap with f.q and f.k, and we also increment Q by 1 and also increment K by 1. And that's it. That's the 3 cases covered. There are no more possibilities. So that's really the bulk of the program derived. And we do have some termination proofs to look at, and we'll do that next. But just before that, it would be worth our while having just a closer look at how this array will be processed using those steps. So if we just have a closer look at the middle of processing, and what we'll actually do is step through an example array and see how these steps actually work. So here we have an array that contains zeros, ones and twos. We've mapped out each of the things that we need to look at. So we're processing at f.q. So this is the one that we're processing currently in the yellow box. I've also given the bound function down here, which is t minus q. And at the moment t minus q, well, that would be equivalent to t minus 0, which would be 10, because remember t is equal to n over here. And I've also laid out the steps that we need to take in each particular case. So if f.q is a 0, remember we're swapping f.q with f.k, and we're incrementing q and k. So when we step through this, what do you need to pay attention to? You need to pay attention to each case and what happens. And also you need to pay attention to the unprocessed segment. You'll see this unprocessed segment will shrink, and also you'll see that the bound function will also shrink. It will be a decreasing function. So as we step through this, we should be able to see that our array gets processed. So the first one was a 0. We're going to increment q and k. The next one is a 2. So we'll need to swap and shift the 2 and bring the 2 down here to the last segment. We now have a 1. So if you can remember, where there's a 1 at f.q, we just simply increment q. The next one is a 2. So again, we need to swap and decrement t. We now have a 0 at f.q. So again, we need to swap and increment both k and q. We have a 1 now, so we just increment q. Another 1, so it's just a simple increment q again. And now we have a 0, so we swap f.q with f.k and increment both k and q. A 0 again, same step again, swap f.q and f.k and increment both. And now we have a 2. It's in the right place already, but the same step applies. We swap with f.t minus 1, which is effectively the same element, but we still carry out the same procedure. And now q equals t at the end of processing, and as you can see, we have split the array into 3 segments. The 0s precede the 1s, and the 1s precede the 2s. And down here you have a bound function that says t, which is t, which is 7, and q, or t, which is 7, and q, which has incremented up to 7. So 7 minus 7 is 0, proving, of course, that the unprocessed segment has now shrunk to a size of 0 because q and t have met in the middle. So the final part of this is to look at the termination proof. The termination proof requires us to have a look at a number of things. The first part is to have a look at initialization. So with our bound function, and remember the bound function that we have is t minus q. So this is our bound function. The greater than 0 part of this is taken from the fact that we started off with n greater than 0. And we include that greater than 0 bit in here in the initialization part. So we initialized q to 0 and we initialized t to n. You might wonder, well, what about k? Well, k isn't part of the bound function. It's only t and q. So we only have to concern ourselves with the variables that are part of the bound function. K actually has no control over the loop. K is an index value that we use to segment the zeros. From 0 to k will be the 0 segment, but it doesn't control the loop and it's not part of the bound function. So for termination, k is kind of irrelevant. So we take what we substitute q for at the beginning and we take what we substitute t for at the beginning and we put that into our initialization proof. So where there's a t, we are going to replace that with an n. Where there's a q, we're going to replace that with a 0. So t is going to be replaced with n and q is going to be replaced with 0. So we get n minus 0 greater than 0. Through arithmetic, we know that n minus 0 is n, so we get n greater than 0. And that follows from what we were given at the beginning of the program in our specification. The next part of termination is to look at what happens to the variables that control the loop in the loop body. Now, again, k doesn't play a role for controlling the loop and it's not part of the bound function. So it doesn't really matter what happens to k. What matters is what happens to q and t. So there are 3 cases. Each case we went through previously. So if it's a 0, if it's a 1, or if f.q is a 2. If f.q is a 0, well, we incremented k and q. Since k has no role in the bound function, it's only what happens to q that matters. So we take our bound function and we take what happens to q and we substitute that in to our bound function. So wherever there's a q, it's going to be replaced with a q plus 1. So bracketing it off, just to make things absolutely clear, there was a q here and now we're replacing it with q plus 1. By arithmetic, t minus q plus 1 is the same as saying t minus q minus 1. So if we take q away from t and then take another 1 away from that, that's the same as adding 1 to q and taking it away in one go. So remember, we're looking for a decreasing function. And t minus q minus 1 is always going to be less than t minus q. So this step of incrementing q guarantees that we have a decreasing function. Now in the case that f.q is 1, the 1 is already in the right place. So remember, we didn't do any swapping, we just incremented q. And we do exactly the same step here. In fact, we can just literally rewrite the whole thing out again and say or even state that, look, it's the same as the first case. We just increment q, and by incrementing q, we again have a decreasing function. So what we're really just showing is that in each of the cases, something happens to q and something happens to t, and we need to ensure that what happens in each case gives us a decreasing function. Now, of course, in the final situation where we have f dot q equal to 2, something different happens. We don't increment q, we decrement t. So we need to take our bound function and substitute what happens to t into the bound function. So wherever there's a t, it's going to be replaced with t minus 1. So here's the t, that's part of the bound function, and we replace that with t minus 1. Straightforward substitution. Wherever there's a t, put in a t minus 1. I bracket it off to make things clear so that you can see where the substitution took place. To make things a little clearer and get rid of the brackets and simplify things a little bit, bring the terms together and bring the numbers kind of to one side, we can just rearrange this. We know that arithmetically that the brackets don't make any sense here, and we can rearrange the numbers because everything's separated with a minus symbol. This could be using our commutativity and associativity laws to rearrange those components so that we have t minus q minus 1, and quite clearly t minus q minus 1 is less than t minus q. Once again showing that what we're doing to t guarantees that we have a decreasing function. The final stage is to rewrite everything out as a full program. So if you look at the full program, well, we still have our constant, we still have our variable section, our array is defined as it was in the specification. We have an assertion to state that the array contains only zeros, ones, and twos. We now have 3 variables, so we kind of define or we declare 3 variables, k, q, and t, and we initialize those. Now our initializations of k, q, and t here, we've derived that. That isn't being plucked from thin air. We've already derived that and proved that that's the case. The next thing we do is we write our loop. And remember the guard on the loop, this q less than t, again, that hasn't been plucked from thin air. We derived that as well. Now, each of the cases inside the loop body, of course, we derived those. We looked at what happens if it's f dot q equal to 0. Well, we know we swap f dot q and f dot k and increment both q and k. If f dot q is equal to 1, there's no swap involved. It's a simple incrementation of q. And where f dot q is equal to 2, well then we swap f dot q with f dot t minus 1 and we decrement t. So it's just really writing out all of the bits that we've derived into one whole program. And you can see the template that we kind of started off with in the specification is used to do that. In fact, all of this kind of middle part of the code, this segment here, well, all of that segment was really S in the specification. So we're really just replacing all of the code that we've derived and putting it in where S was in the specification. Of course, our post condition doesn't change because we've derived the program from the post condition. So by doing that, we've guaranteed that we have a solution that meets the post condition.